Right, so let's just check this is actually recording. Yeah, we are recording. We are good. So you were given your assessment on Wednesday. Hopefully you've had time to sit and go through it. Maybe you've even printed off the mark scheme and marked it yourself. Well, in this video, I'm going to walk you through the assessment. Yes, I'm going to use a mark scheme, but I'm also going to try and use this video as a way of recapping everything we've done and introducing or recalling a lot of the terminology that we've previously used as a way of making this assessment not just something to test yourself by, but to help you progress and consolidate what you've learned. That's the idea. I'd really like you to have the mark scheme in front of you when you're doing it, and I'd really like you to have your test in front of you so you can correct it in green pen. Now, question 1. What type of substance might a saucepan be made from? You'll have seen on the mark scheme that we've got copper, aluminium or steel. I'd like you to be thinking, though, when you're answering that question, about the properties of these materials. I don't want you to answer that question just by recalling what your own saucepans in your kitchen are made from. I want you to be thinking of the term malleable, which means we can shape the metal into whatever shape we want. And I want you to be thinking of the term thermal conductor, or they have a high thermal conductivity. They can conduct heat very, very well. Those are the two properties I wanted you to be thinking of in that question. Question 1b is another properties question. Why is glass used to make windows? Well, the mark scheme says it's transparent, it's strong, it's waterproof, and all those things are correct. Other properties might be that it's got a high melting point, for example, and when glass in a greenhouse gets hot, it doesn't start to melt. Another property glass has, which isn't necessarily why we use it to make windows, but another property it has is it's brittle. And if you don't know what brittle means, a lot of people think that brittle just means very easy to break. You know, they might think of like brittle bone disease and know that people with brittle bone disease break the bones very easily. But brittle doesn't mean easy to break. What brittle means is, in the form of glass, I can take a sheet of glass and I can push on it and I can push on it and I can push on it, and it's not going to deform. It's not going to slowly start to bend like a sheet of metal might. A sheet of metal might slowly start to bend as I apply a force to it. The glass won't do that. It won't deform up until we get to the point where it just suddenly shatters. That's what brittle is. You can be strong and brittle. Tempered glass is extremely strong. Go on YouTube and look how strong tempered glass is. It's very, very strong. It won't show any signs of deformity, but it is brittle. It will just smash at some point without that deformation first. Question 2 is another question based on properties. We've got 6 things here and you've got to put them into 2 different groups. 1 mark for putting them into 2 groups, 1 mark for your choice. Now the group I would have chosen, and the one that's on the mark scheme, is glass, steel and stone in one group and cotton, leather and wool in another group. The reason I would have chosen perhaps density as so how hard they are, how much mass there is per unit volume. I would have perhaps chosen density as the reason. We could have also used how good an insulator they are as well. So for example, cotton, wool and leather all trap air, so they can insulate things really, really well. Let me know we have comments disabled, don't we? Let me know by email if you've got something different. When we look down here, question 3, what is the name of the first group of elements in the table? What that doesn't mean is in the periodic table. In the periodic table, the first group is group 1, or the alkali metals. It obviously means this table here. And to be honest, even just by looking at the names of group 2 and 3, where we've got liquids and gases, you'll probably put solids as group 1. But I just want to point out, some of you may have looked at that and seen copper and seen aluminium, and you may have been tempted to write the word metal. Well, remember we talked in the topic about the periodic table. We said that we have a zigzag line in the periodic table, and anything to the left of that zigzag line is a metal, and anything to the right of that zigzag line is a non-metal. And if we have a look here, aluminium, sulfur, copper, sulfur lies to the right of that zigzag line. Sulfur is not a metal, so it can't be A. The answer was C. They were solids, and really that should be solids at room temperature, because remember, every substance has the ability to be a liquid, solid or gas depending on the temperature. So when we see questions like this, we're assuming that we're talking about room temperature. What is the name of another element that will fit into group 3? Well, if we have a look at group 3, we've got gases at room temperature. And we know that the only gas at room temperature there is hydrogen. Let's have a look at some of the others, see if there's anything I can tell you about those. Not a great deal. Carbon is on the right-hand side of that zigzag line, which makes it a non-metal. Iron and magnesium are metals, but that's by the by. Question C. What property makes copper and aluminium suitable to be used in electrical cables? Well, if you have a look at the mark scheme, you've got a few. You've got they can conduct electricity. You've got they are strong, they are flexible. All those are fine. But we used a word in one of the previous videos beginning with a D, and I'm hopeful that you're remembering and you're thinking, ductile. Ductile is a property of a metal that allows it to be spun out into wires, which is obviously highly important when we're making electrical cables. So copper and aluminium, yes, they are good conductors of electricity. They are strong, they are flexible, but they're also ductile, which would have been another word hopefully you can now recall a bit better. List of substances which are metals. So 4A, take your periodic table, have a look at that zigzag line. Third time I'm saying this now, and see which side of the zigzag line they fall on. Aluminium falls on the left. Iron falls on the left. Silver falls on the left. They are your metals. Carbon dioxide you won't even find on the periodic table because it's not an element, it's a compound. Remember the difference between an element and a compound. A compound is two different elements chemically bonded together. Question 4B, describe two properties of non-metals. Well, the mark scheme mentions low melting point. It mentions brittle, which is what we talked about before. It's a poor conductor of heat, a poor conductor of electricity. Now they tend also to have, we've got low melting point in there, low boiling point as well. A lot of the non-metals like oxygen, nitrogen are already gases. They've already boiled by the time we even get to room temperature. You know, by the time we get to, 0 degrees, 20 degrees C, they've already boiled. So a low boiling point will have done as well. Now, just to highlight, we tend to say that non-metals are poor conductors of electricity or good insulators. There was the exception we talked about when we were looking at properties of metals and non-metals, and that was graphite or graphene, which is carbon. And carbon is a non-metal, but in the form of graphite and graphene, it can conduct electricity. That's a good exception for you to remember. That'll come up a lot. 4C, what substances are the two main gases in the air? Well, it's oxygen and nitrogen, but not in that order. A lot of people come up from primary school and think oxygen is the gas we breathe in, therefore there's loads of oxygen around us. Oxygen is only about 21% of the atmosphere. Nitrogen is about 78%. And if you do a bit of basic maths, that tells you that all the other gases make up less than 1%. Question D, which substance is a compound? Well, we answered that when I went through them. That was carbon dioxide, because it is made of two different elements, two different types of atom, chemically bonded, carbon and oxygen. That's why it makes it a compound. Give two observations that would show a chemical reaction is happening. In the very last video I mentioned this, so let's go over a few. Well, I'll give you what the mark scheme says and then I'll see if I can think of any more. Colour change, gas given out, solid formed. Alright, so we could have any of those. We could have a colour change, bubbles, or a precipitate. When it says a solid being formed, we're talking about a precipitate. Like the carbon dioxide we talked about in the last video going into the lime water would produce a white solid, a white precipitate. It's totally left off temperature change on that mark scheme. So I mentioned in the last video that if the temperature increases, if heat is given out, that's an exothermic reaction. If the temperature drops, it's an endothermic reaction. So if you've remembered that from the video, give yourself the mark for that as well. So a temperature change is also important. I also said in the last video that something might look like it's dissolving away. So I might put some magnesium into some acid and it looks like it's dissolving. But here's where we've got to be really, really careful. Dissolving itself is a physical process. I can dissolve sugar in water, but I can then evaporate the water off and leave all the sugar behind. If I take some magnesium and put it in acid and it looks like it's dissolving, if I evaporate the liquid off, I'm not left with my magnesium, I'm not left with my metal. So although they appear to do the same thing, dissolving isn't necessarily a sign of a chemical reaction. It would be in the case of the magnesium and the acid, but not in the case of the sugar and the water, because I'm not creating anything new. It's a physical process in dissolving. So you can't, and I think I stressed that in the video, so you can't have, it looks like it dissolves. One example of an everyday reaction, my word, there's so many. Making toast, frying eggs, anything to do with cooking, baking a cake. You know, you make some toast, you take it out the toaster, you're not getting that back into bread. You have made a new substance, you've oxidized the chemicals in that bread, and you've created something new. What else could we have? Rusting is on the mark scheme as well, of course, oxidation of iron. And burning, of course, combustion, when something sets on fire. Again, that's an oxidation reaction. So rusting and burning, or when things combine with oxygen. Rusting or corrosion happens over a long period of time. When we burn something, we use heat to speed that process up. So they're both oxidation reactions. And I think cooking was a good one. I don't think there's too much more to say about that. Right. Describe the difference between a mixture and a pure substance. Well, when we talked about mixtures and pure substance, we learned examples. We said that the air was a mixture, for example. We said that a solution was a mixture. I could take some salt and I could put it in water. And what have they both got in common? Well, like we said before with the salt and water, I'm not reacting the two together or making something new. I'm just putting the salt in the water and I have two substances there, but they are not chemically combined. The air around us has lots of different substances. It's got oxygen, it's got carbon dioxide, it's got helium, it's got hydrogen. And although, for example, in carbon dioxide, I have oxygen combined to the carbon dioxide itself isn't combined with hydrogen, and it's not combined with nitrogen. So a mixture is where we have more than one substance, but those substances are not chemically combined together. And it says pretty much similar on the mark scheme, but hopefully that explanation's cleared things up for you. Question 5. Now, when we're looking at the symbols for elements, we've got to be a little bit careful that not all the elements have symbols that are a reflection of the first letter of that element. Hydrogen does. Hydrogen is simply H. Quite often, and that'll be what we see on the periodic table, H. When you're looking at a word equation or a symbol equation or formula equation for a chemical reaction, you might often see hydrogen represented as H2, which means two hydrogens bonded together. And that's how hydrogen exists in the atmosphere. That's how hydrogen actually exists as a gas, with two of them put together. So H2 would be the formula for a hydrogen molecule that we find in hydrogen gas, but a hydrogen atom would just be H. And the one that we see on the periodic table is just the atom, so that's H. Copper is Cu. Now, obviously, there's no U in the word copper, so that's sort of a little exception. Magnesium, I hope we all recognise magnesium, and chlorine. Now, when we look at magnesium and chlorine, I want you to notice that the second letter is a lowercase letter. Magnesium is one element, but because we've got two letters to represent it, the second letter is a lowercase letter. Same with copper, Cu. The U will be a lowercase letter, so we don't confuse the C and the U as being two different elements. In carbon dioxide, we have a capital C and a capital O, or capital C and then an O2, the O being a capital. They are both capitals to show us that we actually have two different elements. But if I had a lowercase o, a capital C and a lowercase o, well, that's just one element. That's actually cobalt. So just, if we didn't pick that up in the lessons, that second letter being lowercase is really important. Question B, explain an advantage for using an internationally agreed system for elements. Well, we said in the videos, it just helps people communicate. People speak different languages, and how, you know, without learning all the names for all the different elements and the symbols in a foreign language, it would be very, very difficult to communicate with somebody unless we have this internationally agreed system. So any kind of answer there that implies it's just easier to understand what people in other countries are talking about, it's easier for communication, that would be great. Question 6. Match the correct diagram to each description. Well, let's talk through the boxes first and then we'll go to the description. Let's see what I see. In this one here, in box A, I see, excuse me, I see a compound. I see a dark circle representing one type of atom, flanked by two light circles. It could maybe carbon dioxide, perhaps, with the carbon being the dark one. But I only see the same repeating molecule over and over. So that's just a single compound. If I look at B, and then we'll match these up in a minute, but if I look at B, I see the same atoms now, but they're not chemically combined. I see the dark circles just on their own, so that's one type of element, and I see the light circles bonded together to make a molecule, but those molecules are elements because they are made of just one type of atom. So here I see a mixture, and I would say it's a mixture of two different elements. I have the dark element and I have the light element. So I'd say that's that one. Question C, we have the compound, which is a dark circle, and the light circle. Hopefully you can see where my mouse is. And we also have the element here, which isn't combined to the compound. So this is a mixture of an element and a compound. And D is just an element. So molecules of an element is going to be D. These are molecules because it's two atoms stuck together. Molecules of a compound will be A. A mixture of different elements is going to be B. Right? Even though these are combined as molecules, they are still elements because within those molecules there's only one type of atom. And D, a mixture of an element and a compound is going to be B. A mixture of an element and a compound is going to be C. The compound is this little molecule here, and the element is a dark circle. Right. Complete the bar chart to show all the substances in glass. Now, there's a couple of rules with the bar chart. It's only worth 1 mark. But what I want you to, when you're given a question like this, is I want you to think about conservation of width. All right? I've just made that term up. Don't go into your maths lesson and start talking about conservation of width. It's just the way I like to explain it. If I'm given a bar chart and I'm asked to complete it, I'm going to look at how wide the bars are. And then when I draw my other bars, I'm going to make them the same width. Now, there's no mark for that on this, but it's something I think that's important going forward. Because there are types of charts, types of graphs, where the width of the bar itself helps represent a quantity. Okay, it has a meaning. And I'm sure you'll pick that up further down the line in maths. I'm not going to go into that here. But just make sure the bars are drawn the same width. Calcium oxide needs to be drawn to 10, so it should be drawn to this line here. And other is 5. Now, obviously, there's a degree of estimation here because we don't have a line opposite number 5 to follow, so it should be about halfway up. That should be, I'd be surprised if many of us didn't get that one. So that's just an easy 1 mark. Now, what other type of chart could we use to represent this data? Well, this type of data, if we have a look at it, is categoric data. What do I mean by categoric data? Well, when I look at a table, in one of the columns, I have words, and in the other column, I have numbers. And that's not always going to be the same. I'm sure everybody in school has done maybe the paper helicopter experiment, where you measure the length of a wing, and then you time how long it takes a helicopter to drop. And in that instance, the length of the wing will be measured in numbers on the left, and the time taken to drop will be measured in numbers on the right. And when we have both columns that are numbers, we call that continuous data. And we always use that, a scatter graph for that in science. When one of the columns is words, that's categoric data, or non-continuous, or discrete. There's a few terms for it, and we use a pie chart or a bar chart for that. So I wouldn't use a line or a scatter graph because they are for continuous data. And cartoon, I think, is just in there as a red herring. Question C. Which element do the top 3 compounds in the table all contain? Well, let's go back up and have a look. The top 3, silicon dioxide, sodium sulfate, calcium oxide. You may look at that and to start with think, oh, I'm not sure, there's not an obvious common element. Actually, there is. Silicon dioxide contains oxygen, calcium oxide contains oxygen, and sulfate is a group, it's a compound group. It's not an element. If you were to look for sulfate on the periodic table, you wouldn't find it. You'd find, if you Googled sulfate, you'd find a group that contains oxygen. So oxygen is what they all have in common. Now, when we look at question C, oxygen is answer C. Don't put oxide. Oxide isn't an element. When we react something with oxygen, we do give it the last name, oxide, but an oxide isn't an element. Oxygen is. Question D. Word equation. We did this just in the last video. Calcium oxide is made by heating calcium carbonate strongly for some time. This is the exact example we did. So how am I going to write a word equation? Well, remember we said we start off with the ingredients. And the ingredient here is the calcium carbonate. That's the thing we're heating. So I'm going to write calcium carbonate. And then I'm going to draw an arrow. I might even write the word heat above the arrow. Let's see if that was needed in the mark scheme. No, it wasn't. Okay. So I might draw the word, write the word heat above the arrow just to show that's what I'm doing. But I'm going to have calcium carbonate and I'm going to draw a line. And I need to then think of what to put on the other side of that line. Well, the question tells me calcium oxide, right? But in the last video, we talked about what happens when we heat carbonates and we also produce carbon dioxide. So it will be calcium carbonate, arrow to calcium oxide plus carbon dioxide. And the breakdown of the marks would be 1 mark for getting calcium carbonate, arrow, calcium oxide, and then your second mark for remembering that carbon dioxide is also a product. So I have to blow my nose, sorry. There you go. But that was interesting to watch. Question 8. Which one of Plato's 4 elements is not a substance? Well, if we have a look here, earth, fire, earth, and water, quite commonly known as being the ancient elements. Fire is the one that's not a substance. It's very difficult to explain what fire actually is. We'll talk about the others first and then we'll come to fire. Air is obviously a mixture of different gases, right? It's a physical substance. The earth is a physical substance. You can stand on it. Water is a physical substance. You can wash your hands with it. Fire seems to be far more difficult to define, and it is. But essentially fire, we are going to think of it at the minute as being energy. Energy that is being emitted from a hot gas in the form of light and in the form of heat. It's not a physical substance I can grab. You might be able to see a flame, but all you're really seeing is the gas getting very, very bright as it's giving off that heat and light. That's all you're really seeing. The flame, the fire itself doesn't exist. Give a modern description of an element. Whoa. Write about atoms in your answer. Well, let's have a look at what the mark scheme actually says, word for word. It just says all the atoms in an element are the same. I think on the videos I made, I said that an element contains only one type of atom. So you've put that down. As long as your answer implies that whatever atom you've got in the element, all the other atoms are identical to it, fine. Okay. Right, next question. Question 9. Some of the main properties of metals are listed below. What does flexible mean? Well, we talked before about brittle, and flexible is the opposite of brittle, right? It means it can be bent without breaking, right? Whereas with glass, I can push on it and I can push on it, I can push on it, and it won't bend, then it will snap, it will just smash. That's brittle. Flexible is the opposite. I can literally bend something and it won't break. All right. That doesn't mean if I let go, it's going to bounce back into position. That would be more an elastic property, but at least it's not going to break. Okay, we are there. The last question. State the name of a metal and one use of the metal. Oh, there are so many we could use. Now, there's 2 marks for this. One of them is for choosing a suitable metal. And let's just have a look. Bridges, because it... Okay, so one of the marks, is for not just naming the metal, but giving its use, or giving the use of metal. The other one is for linking that with the properties. So I might say gold is used for jewellery. 1 mark, that is a use of the metal. The property is it's not very reactive, so it's not going to corrode or rust over time. 2nd mark. I might say iron is used for building bridges, okay, which is 1 mark. And the reason for that is it's strong, so it can handle the weight of cars going over it. 2 marks. I might say that copper is used in water pipes. 1 mark. Because it doesn't react with water, it's not very reactive, so it won't corrode. 2 marks. I might say copper is used to make electrical wire. 1 mark. Because it's ductile and can be spun into fibres, or because it's flexible, or because it's a good electrical conductor. 2 marks. You get the idea. If you're not sure if you've given a proper example, give us an email and I'll let you know whether you should get the mark for that or not. But that's it. So, goodbye.